Syzygy episode 33, bigger Goldilocks zones around binary stars. And welcome to episode 33 of Syzygy. Hard to believe we got this far, Emily. 33 episodes. It took us this long to actually get a guest in the studio. And by studio, I mean your office.
Yeah, it's quite a difficult office to find, Chris, to be fair.
Well, yes. But if we'd invited more guests and they'd had difficulty finding the office, that'd be a reasonable excuse. But we haven't done that. This is the first time. Why has it taken us this long? This is silly.
Well, but we've got a 100% success rate for people we do invite now.
I like your framing. That was very well done. Top points. 5 points for Gryffindor there. So, yeah, episode 33. And in this episode, we're going to be talking about a little bit of research that's been done recently. Published, recently, like in the not too distant past.
It was Thursday night this came out. Yeah.
Thursday night. And the thing that blows me away the most about this research is not just that it's really kind of cool. It's not just that it's new. It's that it was done by someone who I'm looking at opposite me here at the Syzygy table, who is earlier in her career than I could even conceive of a publication actually being a reality. Would you please make welcome to the Syzygy round table, Bethany Wooten. Hi, Bethany.
Hello there.
Thanks for joining us as our very first guest ever on the show. Bethany, tell us a little bit about yourself. You're not an undergrad anymore.
No. I don't have that name to myself anymore. No.
So what are you now? You're a master. You're a mistress.
Yes, I have a master's. Yes, I'm a master of physics.
But the reason I asked that is because when this research was done, you were an undergraduate student. Yes. Is that normal? Do undergraduates normally publish research?
Well, I mean, yes and no. It depends what you find out. It depends what your supervisor deems useful things for you to look at. And just so happened that the thing that he deemed useful to look at was actually kind of useful for publication and was good enough for publication.
So that was pretty good for you. Emily, did you ever get anything published when you were an undergraduate?
No. I was well into my PhD before I started publishing.
Mm-hmm. Yeah, me too. So you're well ahead of the two of us, and so you're redefining normal, I think. Anyone out there who's listening to this who is in their undergraduate, come on, pull your socks off. Pull your socks off? Pull your socks up.
No, don't pull them off. This is quite a small office.
Oh. Tell you what, my brain is really struggling today, but we will push on and we will get through. So we're going to have a bit of a chat about this amazing research that Bethany got published. But before we do that, Emily, there's been a little bit of excitement in your part of the world this week. It's a very special anniversary for something you hold very dear. Tell us about it.
Yeah, so it is a special birthday today.
Hooray! Whose birthday?
It's not my birthday.
Oh.
It is the Astro Campus's birthday.
Astro Campus, which is a very special thing here at York. Tell us about Astro Campus. It's your baby.
It is. So Astro Campus is our observatory here on site at the university, and it's used for undergraduate students to use during their teaching program, but it's also massively part of our outreach program as well. So that means that lots of people from the public to brownies and guide groups, community groups, schools, they all come and visit us as well. And actually, this is kind of a nice link to what Bethany does now, because she is our graduate intern who looks after our outreach program.
Cool. So you spend a lot of time over at Astro Campus.
I do.
It's
a great place.
What's over there? I mean, I'm imagining telescopes, but it's got to be more complicated than just, a telescope on a tripod out on the lawn. So what's at Astro Campus?
You're absolutely right. You've got lots of telescopes, lots of nice big telescopes for everyone to have a look at. You've also got the Astro Capsule, which is quite a nice little building that you can go in and read.
That sounds fancy. What's in the Astro Capsule?
Oh, there's lots of things, lots of pictures and lots of things to read about, all about space. You can have a little look around. Yeah, it's really nice.
Are these all sort of traditional stick your eye up to the eyepiece kind of telescopes, or are there a range of different kinds? What do you got over there?
Yeah, well, I mean, you can fix an eyepiece onto the telescopes, but you can also take pictures using CCD.
You can do that
if
you want.
You can do that if you want to. I mean, when it's actually clear, you can absolutely use your eyepiece. But yeah, you can also take pictures using cameras and things like that. Lots of different things.
But there's a dish over there, which that's not an optical telescope, and there's a bunch of things that just look like big poles, like flag poles. That's not an optical telescope. There's more to it than that.
Yeah, so we've got lots of radio dishes as well. So we've got 2 3-meter dishes, which are the ones that you're talking about. They look, they're kind of mini versions of the bigger professional radio dishes like Jodrell Bank has. And we also have the dipoles, which are very simple dipole antennas.
Those are the flagpoles.
Yep. And again, they're looking for radio signals, just a slightly different frequency. So we've got lots of different bits of equipment that we can play with. And it's 5 years today that whole site has been open. We had our official opening in March of 2014.
Wow. Gosh, they grow up so quickly,
They
don't
do.
they? Hey?
Yeah, these little Astro campuses.
So over those 5 years, roughly how many people do you reckon have come through Astro Campus? I guess it was mainly school groups and community groups?
Mainly, well, that's the easiest way to count because that's where you get the big groups coming through. So we're looking at a few thousand people have come through, as well as we've had just general open days, including university open days. We had a solar eclipse. We had the transit of Mercury. We've had all sorts of fantastic events over those 5 years. And the site's changed dramatically. The telescopes have changed dramatically. We've been able to make huge improvements. So it's so exciting when I look back at the photos from 5 years ago, just how much has changed.
Yeah, very nice. Very nice. Well, as you say, that's a kind of a nice lead in to the main topic of the day, which is, Bethany, that's your research. So Emily, you're the one who decided that this would be a good topic for today, and I agree wholeheartedly. But what was it about this that made you raise an eyebrow and go, we should talk about this?
Well, I think there were two things that really kicked it off for me. So I was very, very lucky. I got to see the press release while it was still an embargo. Ooh. And I had to sort of sit on my hands and say, this is really cool, but I can't tell anyone.
I need to tell someone.
But let's have a syzygy recording about a thing that might
Trust me, Chris, we have a topic for Monday. Don't worry about it.
So I was super excited. And I was super excited because I think binary stars are super, super interesting. Planets are super, super interesting. Habitable planets are kind of like the most interesting.
And this one's got it all. This has got everything going on.
Yeah, and then the wonderful, to have a student involved at research at this level is just amazing. I mean, how many students get press releases put out about their research?
I know.
So
I mean,
cool.
you know, we're both just ludicrously jealous about this, so, forgive us that. Okay, so let's find our way into this story then. You just listed a whole bunch of things: binary planets, or binary star systems, planets, habitable zones, Goldilocks zones. It's got everything. Where do we start? How do we unpack this little bit of research? And can we start with, first of all, where has this been published?
Published in so we call MNRAS, so the monthly notices of the Royal Astronomical Society.
Which sounds pretty impressive. Oh yeah, just this thing I had in the monthly notices.
Just the UK's premier astronomical journal.
I'll just leave that there on the coffee table for anyone to peruse. Okay, Bethany, I'm going to throw this one to you. Give us your elevator pitch. What is this research? What's happened? What have you found?
So, basically lots of stars. So when stars are young, they form not in isolation, but they form in groups. And lots of those stars form in binaries, so they're binary systems, two stars going around one another. And so you can still get planets going around these binary systems. Some of them are still stable. But in these early really young star systems, you get lots and lots of stars whizzing past you. It's very sort of chaotic. Lots of things are happening. Lots of dynamic stuff's happening. And these binary systems, they don't stay the same separation. Some of them move close together, some of them get torn apart. Lots of different things happen. But some of them you'll find a star will whiz past a binary system and it will bring the two stars closer together. And in some instances, this can actually increase the habitable zone around the binary stars. So if you did have a planet going around these two stars, it would actually get bigger sometimes.
Okay, so my brain is piecing all of this together. So what I just took away from what you said there was that in a really chaotic early sort of star formation kind of period, in a what do they call stellar nursery, right? Lots of stars and stuff being made. That sounds to me like absolute bloody chaos. But what you're saying is that under some circumstances, you can have a binary system, and then another star comes nearby and actually improves the situation from the point of view of habitable zones.
Yes, exactly.
Is that vaguely right?
Yeah, absolutely.
Okay.
Yeah.
So we need to talk about, pull this apart a few pieces at a time. So let's start with binary systems. Now, we've talked about this a bit before, Emily, and it came as a bit of a surprise to me that binary systems are actually much more the norm than one might think. That we have grown up around a single star, the sun, and so that to us is normal. And surely something as weird and as complex as a binary system like you see on Tatooine in Star Wars, that could never happen. And apparently it happens all the time.
It does happen all the time. So we know that in our galaxy, amongst the kind of ordinary stars like the sun, maybe 1 in every 2 stars is part of a binary, maybe even a trinary. I think we're up to about 7 stars in one system. I mean, this is getting really crazy by this point.
I mean, what we're talking about is stars which are all... it's not like there's one big star in the middle and they're all going around that. You're talking about stars which are orbiting around some kind of common center, a common center of mass. But you can have relatively vaguely-ish stable systems, up to 7 of those?
Yeah, they come in pairs by that point. So
right.
you
so
sort of have...
You get like a hierarchy, yeah.
Wow.
Yeah.
And does it tend to be like a pair orbiting a... I mean, I guess they're all orbiting a common center, aren't they? But is it a sort of a pair orbiting a pair orbiting a pair? Or...
Yeah, there's no apples involved at all.
Kill me. Right. No, seriously, though. I mean, I'm imagining sort of these binary systems in orbit around each other.
Yeah. So once you've got a pair of a binary pair, then that whole binary pair might be in kind of another binary pair with another. So we've got 4, 2 pairs, 2 twos, basically going around.
I mean, that just blows my mind. Okay, so this is much more common than you would think. Okay, so in an early period of star formation in a stellar nursery, then we have a binary system. Great.
Yeah.
Fantastic. And you can have planets around binary systems. So let's talk about that for a second. It still blows my mind that you could have a stable planetary orbit with a binary system. So help me just imagine this. Are we talking about a planet that's going around 2 stars at once, or are we talking about a planet that's going around one of the stars that's then going around another? Help me.
Okay, so you can have both of the things that you described there.
Right.
So you can have a planet just going around one of the stars, and then the stars orbit each other, or you can have a planet that goes around both of the stars simultaneously.
Right.
So the first type, the type when you're just going around one of the stars, is called an S-type planet. And then the second type, where you're going around both of the stars, is called a P-type planet.
And that's stable, is it?
It depends on your orbit.
Doesn't sound stable, but...
It depends. If you're quite close in, so if you're about the same distance the Earth is from the Sun, so 1 AU, you can get quite a lot of these stable planets. If you're talking about going out to sort of like 50 AU, and it gets a little bit less stable. So you've got to be really quite close into your planet. But that's not necessarily bad for life in the sense that...
Okay, help me get a sense of scale there, then here. When we're talking about a binary star system, and I know that these things can vary by enormous amounts, but what's the distance between the stars? Like if I think of the Earth going around the Sun at 1 AU, by definition, the mean distance of the Earth from the Sun, that's how we define that, then that to me is reasonably close. But when I picture a binary star in my mind, I'm still picturing it a little bit like a star in a planetary orbit around another star. So what kind of distances are we talking about? How far apart are the stars in a binary system?
I can't actually remember what the specific average is, but it can range anything from sort of like 1 astronomical unit, so Earth to Sun.
Earth distance.
Earth distance to all the way up to about 1,000. But obviously at that distance, you can quite easily get torn apart by a third star coming in. It's very easy to break apart that kind of system because it's so far apart.
Right. And scale of the solar system, just remind me, the outer planets, how many AU are they away?
Tens of AU.
Tens of AU. Yeah. Okay. So you could have a binary star system where the star is as close as the Earth or as far away as way out beyond the distant planets. Okay. All right. So I can then now begin to picture a planet going around a star like we are going around the Sun, and then another star way out there, which is the whole system is a binary system. Okay. You're also saying, though, that you could have a planet going around both stars at once.
Yes, and that would be, in order to have that stable, you need to be further away.
Right.
So if you got too close, then things would go a bit chaotic. But as long as you were far enough away from those 2 stars at the centre, you'd be absolutely fine.
Okay.
Nice and stable.
All right, so we're building up this picture. We have a binary system and we have some planets or a planet. Now let's talk habitable zones. All right, we're building up this stage at a time. Habitable zones. What defines a habitable zone around a star?
So, well, we interchange the words here between habitable zones and Goldilocks zones.
Yes.
Goldilocks is kind of what we thought the public might like. It's a very easy reference to pick up. Basically, you want your planet to be not so hot that all the water boils away, but not so cold that it all freezes out and you've just got Iceland.
Yeah, not too hot, not too cold, just right. Perfect. Just like Goldilocks and her porridge. Yep.
But I think actually people kind of get what habitable zones are anyway, because
I think we've reached that point.
does what it says on the tin.
Yeah.
It's a zone in which we could be
you live
habitable.
in it? In principle. Yep.
Yeah.
Okay, thumbs up.
So in our solar system, we got this nice disc-shaped habitable zone. It ranges from just outside the orbit of Venus to just a bit further than the orbit of Mars. So it's reasonably large, and that's because it kind of depends on what your atmosphere is like and what conditions you can hold onto liquid water.
Now that's the thing, is it? It's not so hot that the water boils away and not so cold that it freezes. It's water that we're picking on here.
Yeah, because water, as far as we know, is useful for life, or at least necessary for some forms of life that everything else is then dependent on. So if we go for the easiest option of how to find life elsewhere in the universe, we think it probably has to involve water because that's what we have. So we'll start there.
Yeah, you got to go with what you know. Otherwise, you're just making stuff up, which is theoretical physics, not astronomy. So I can say that because I'm a theoretical physicist. That's allowed. I have a card and everything. So habitable zone, we're talking about the region around a star where it's not too hot, it's not too cold. You could have liquid water in principle, depending on the planet and the atmosphere and all of that. Okay, so you could have habitable zones around stars which are in binaries. I think that's a reasonable statement. And it could be around one or both of those stars. Presumably the habitable zone starts looking a little bit more complicated when you've got two stars involved.
Yeah, so you can have a planet. So as long as, if you're talking about in terms of if we've got two stars again and we've got a planet going around just one of them, the planet could go around either star in principle as long as they're far enough apart and things like that. So you can have two habitable zones in the sense of that. But the habitable zone is no longer just dictated by the one star that your planet's going around. You've now got to take into account the fact that the secondary star is there and it's also contributing heat and other things as well. So that will change the shape of your habitable zone because of the presence of the secondary star.
Yeah, just because it's there. I mean, the habitable zone is defined by how hot is it.
Yes.
So if you've got another star in there, that's going to change things.
Yes, exactly, yeah.
Okay, cool. So we're almost there. I kind of feel like we're almost there. We've got binary stars. We've got planets going around them. We've got the habitable zones around those stars individually and collectively. Mm-hmm. And we're at this early stage of formation where we've got a very chaotic environment in this stellar nursery. There's lots of stuff happening, which means there's more than we would see around us now. There's lots of things happening. There's lots of stars being formed. Things are a little bit more closely packed. And under those conditions, interesting things can happen. So take us through that bit. We're going to introduce a third star into the mix now. What happens?
So you've got perhaps your early planet forming around one of your stars. It's happily whizzing around. It's in a stable thing, and the stars are whizzing around each other at a set distance. You've then got a third star that comes in. Depending on the distance of your two binary stars, you can either the two binary stars will move closer together, or sometimes they move further apart.
Right. So that third star is going to come.
The third star comes in, whizzes in, and it
because of its gravity.
Yes,
because of
gravity,
its gravitational attraction, it'll mess things around and perturb that system, push it around. And
so things go a little bit chaotic, and then they sort of get back to sort of being...
Like in my mind's eye, that is a chaotic thing, right? That is another star coming in and just messing things up. Yeah. And in my mind, I'm just seeing the whole thing collapsing. But you're saying it could actually just push the stars a bit closer together.
Yes.
That could happen.
Yes.
Okay. I guess that's possible. I'll take
they
your
get
word
more
for
tightly bound, and they get more tightly bound to one another.
So under those circumstances, what happens to the habitable zone?
So and under those circumstances, your habitable zone may well sort of inflate. So it may get larger because the presence of your secondary star is contributing that bit more heat. So your planet could in theory go that bit further away from your primary star, so the star that it's going around. So you could get a bigger habitable zone in that sense sometimes.
Right. Okay, so you're putting that little caveat on there sometimes. It's not always going to happen, but it could happen sometimes.
Yes, it depends how much closer it gets together and things like that, and the eccentricity of the system as well, which just adds another dimension of what's happening.
So is the point of this bit of research then that this is possible at all? That you've done the simulations to show that you would think that under these circumstances, I mean, it's bad enough as it is, right? But if we're going to throw another star in there, then that really ought to ruin any chances of anything happening at all. But actually, under a small but non-zero number of cases, you can actually get an increase in the size of the habitable zone. And that can help us to understand a bit more about the possibilities out there in the galaxy, in the cosmos, for the number of potentially habitable places. If we have this understanding about when stars are being formed, then that helps us with our guesses about how many cases could this have happened for? Is that the idea?
Yeah, absolutely. I mean, when you look at this chaotic system at the beginning, when all these stars are being created, you think there's absolutely no way that a star, like a planet going around a binary system, should in theory be able to even survive it, or even going further than surviving it, be in its habitable zone for long periods of time. But this shows that it can be, and that's really interesting, because when you're looking at sort of stars, we tend to look at single type stars to try and find planets going around them, but this just shows that perhaps that's not the only route. There could, in theory, be your Tatooine systems you were mentioning earlier, your sort of Star Wars, George Lucas kind of thing. Could be a reality.
Could be
a reality. Could be out there. Yeah.
Okay, so Bethany, this is part of a project that you did. So what is a project, and what were you actually doing to kind of help answer this question?
Yeah, so I mean, a lot of the things that you do when you're thinking about binary systems, thinking that I was just looking at the sky and looking at some binaries, that wasn't technically the case. What I was doing was actually sort of a computer simulation. So I was saying, right, what are the conditions in most star clusters? So that's sort of like very dense stellar nurseries. So how dense are these stellar nurseries? How do they vary? If I vary them, what happens then? Things like that. So lots of different parameters, and seeing what happens to the binaries over a period of about 10 million years. So from when they're sort of first forming and everything's very, very dense, to as the cluster sort of slowly expands over time. And at the end of the 10 million years, how many of those binaries actually survived?
Yeah, so these clusters sound pretty interesting. Are they sort of common things? Is it every star's coming from these clusters, or?
So, yeah, I mean, obviously most stars form in not by themselves, but in a group or something like that. But depending on how many in the group and how dense the cluster is, or how dense the number of stars and in what sort of period of space they're in, that will tell you how they evolve. So they evolve differently depending on how many stars you have inside, which is just it seems strange, but yeah, and things go differently depending on what numbers you put in. So obviously we try and use the ones that we think are most likely, what we see in the sky, but then you can just fiddle about with things and say, what would happen if I if I did this, and then
what if I tweaked these parameters? What would happen then?
Yeah.
So what was it like? I mean, what was it actually like doing a project? Because I'm guessing most of our listeners haven't done a master's in astrophysics. So what is it actually like sitting down and doing this project?
It was a lot of because it was a lot of coding, and I will freely admit that my coding isn't very good. So it was
we all have to start somewhere.
So I had a lot of going, this isn't working, why isn't it working? And then I realised I missed a 1 or a bracket out somewhere, and that would spend days of me just trawling through, because I wasn't good enough to do my code so that it told me when there was an error. So I had to try and find the error, and that was very frustrating. Took hours, but definitely worth it in the end. It came out very nicely.
So you spent, a year on this?
Yeah, so from start to finish. So the first bit was, as I said, like looking at how the cluster evolves, how many binaries actually survive between 0 and 10 million years when you evolve this system in the computer. And then after that, I said, how many planets would survive around those binaries if I did that, and then did the simulations again. And then after that, I then say, right, what if it had a habitable zone around it? Ran the simulation again. And then, right, of those habitable zones, how many of them changed over the course of the 10 million years? Ran the simulation, did it again. So it's building each time. So each little bit was adding a little bit more. And it was basically just how much can you get done in the year? Can you get to that end stage?
Stop when you need to walk out the door.
Yes.
But it must have been a really nice feeling to see the numbers come out, and they're not only plausible, they're interesting.
Yeah.
Often in research you get numbers out which are plausible and boring. That's exactly what we thought it would be, and harumph. Whereas in this case, that's actually really interesting. Yeah,
it's something that we thought from the beginning might be a possibility that these habitable zones did enlarge. But when we were looking at it, it was like, is it going to do it? Is it not? And it was quite nice to sort of be like, wait a minute. My coding wasn't quite good enough. I have to say, my supervisor, Dr. Richard Parker, he actually took my code a little bit further to work out like he could pick them out for a lot easier than I could. I was going through the ones that I thought might have enlarged to find them, and then he was like, maybe if you just did this, it would do it for you.
Yeah, but I mean, that's all right, given that that's his job.
Yeah.
You're a student, no one's paying you to do this.
True.
And he's somewhat more experienced. You'd kind of hope he'd be able to step in and go,
yeah.
Well, here's a slightly different way to think about it.
Yeah.
Otherwise, what's he there for? you know? So I wouldn't feel too bad about that. I think that's okay. That's all right.
So I'm going to ask one of my favourite questions that I ask students when I viva them at the end of projects. So this is when they have an oral exam and they have to defend their work to the academics.
Did you have to do that, by the way?
Yeah, I've already had my viva. I don't want again.
Well, that's all right. Then you can just chill out on this one because there's nothing riding on this other than international notoriety for getting it wrong on a podcast.
Yeah. So spoiler alert, this is one of my favorite viva questions. What would you have done if you had another 3 months to work on this project? How would you have developed it?
All right, so I can answer that one quite easily. So what I did it on was on S-type systems. So that's what I was saying earlier, where just the planet was going around just one of the stars. I'd have loved to do the same research and see if there was anything interesting happening for the P-type systems. So when the planet was going around both stars. I don't think it would be as interesting. I don't think that as much interesting stuff happens, but then what do I know? So another 3 months, it would have been nice to look at that.
What's your gut feeling? What do you think would happen?
Really good.
This is the P-type. The P-type systems are the ones where the planet's going around both.
Yes.
Stars.
So you're now looking at a planet going around both stars, and I think that would probably not be as interesting, just in the sense that if you think about it, if the planet's far enough away from the two stars, it kind of just feels like there's just one star at the center in essence. It's kind of just like having one, star in the middle, which I think is perhaps a little bit.
You're saying in terms of the heating and the radiation, it's already getting all of that anyway.
Yeah, and less interesting things happen in the sense that you've got you can't, when you're talking about earlier, could you have a planet going around both stars? And then what the habitable zones are around both of them. This time you could only have like the one habitable zone because it's just going around both stars. So I'm not saying that they're uninteresting. Obviously they are very interesting. They're just not as interesting as what I was doing. But I reckon that you might be able to see some changes happen between the 10 million years, obviously, like as the stars move in and out. But I don't think it would be as cool.
It'd be worth spending another 3 months.
I think it would be worth spending another 3 months, yeah.
I think if I was to choose one of these systems to go and live on a planet on, I'd definitely pick the S-type.
I'm not sure if that would be, because I was thinking about this the other day, because obviously if you're talking about the Tatooine system, so you've got that famous double sunset going down.
With Luke looking
looking wistfully in the
over the horizon.
That would be sort of your more P-type system, because both the stars set at roughly the same time. Whereas I think if you're an S-type system, you could have this really strange thing where one sun sets and you think, oh, okay, it's time to go to bed, and then another one rises and you're like, oh, rubbish. And then it's just light for far more time. And your sleeping pattern gets messed up.
But my favourite planet's Mercury, right? So what do I know?
Yeah, Emily's not necessarily a good judge of character on this one. There we are.
So you ran your simulations for 10 million years. Yeah. Now, this is quite young, right? I mean, stars hang around for billions and billions of years. So what would happen after a while for these systems?
So obviously as they get older, they sort of break apart from their sort of stellar neighbours, so you don't get so many stars bumping into them all the time. So things are slightly calmer later on in life. So they tend to sort of stay more stable later on, and stars just evolve by themselves in isolation without getting hit into. So if your planet can survive that, the first sort of really horrendous bit in the first sort of early years, then it should be able to survive later on. Maybe life. Who knows?
You can involve some laser-eye cats on your planet quite happily, hopefully. Maybe. Who knows? Cats are quite evil, so maybe that's not a good idea. So if we were to then go and look for these kinds of systems, where would we go and look? I mean, I'm an observer. I just want to go out and find these now with my telescopes. So what do we need to look for?
In terms of, are you talking about in terms of finding the planets themselves?
Or examples of these stars that might have been in these kind of early
I guess you're not going to know now which were the systems that got perturbed, got influenced way back. But if I'm reading you right, what this is saying is that there might be more systems where there is a larger habitable zone? Like, is that the idea? That there might be now more systems than we perhaps thought, where the stars are a bit closer together because they've been bumped around. And that means that the habitable zone is larger. Yeah.
Pretty much, yeah.
Okay. So going out and looking for binary systems and checking out where the planets are, does that mean we might expect then, from an observational point of view, to find more planets in the habitable zone? Like, is that... I don't know. I'm looking at both of you because one of you's done the modelling and one of you's an observer. So help me out here. What do I know?
I don't think that the statistics say that you're likely to find more per se, more that it's just a possibility.
Right.
If you see what I mean. So it's in terms of like the fact of we haven't seen many planets around binaries, but is that because they're not there or we're not really looking for them? I don't know. As an observer, I'm sure you know more whether you're...
Well, yeah, I mean, we have found some. I mean, there's been a few Kepler, the Kepler-Tatooine planet is a very, very famous example. I think what inspires me about this research is that we've got the possibility... when we first started finding planets, we thought, planets around binary stars, that's not going to happen. The gravity is going to throw them out. It's just, you can't get stable systems.
Yeah, that's the naive looking viewpoint that I have, which you're saying that astronomy moved on from that quite some time ago.
Yeah,
and I've just been left behind.
We found planets and we were able to model them, and we even found planets around binary systems very close to home, like the Alpha Centauri system. So then now what this research is doing is saying that's not only possible to have these planets and these to survive around these binary stars, but the habitable zones may be actually a bit bigger than we originally imagined, which to me says that the probability of there being a habitable planet around these systems has now increased. And now I'm suddenly a lot more excited about binary stars and habitable zones than I used to be. So as an observer, maybe we should be out there hunting down more of these binary stars, finding more systems that are both S-type and P-types, I think, and not being discouraged that they're not going to have planets that might have life, but actually there's ways and routes in which some of them may well have life-hosting planets.
I can see a grant proposal here. I can see a PhD possibility. You interested? You planning on doing a PhD, are you?
Maybe
take a bit of time off first. Yeah. Okay. I think you two need to get your heads together and figure that one out.
Yeah. We'll just NASA. We'll give them a ring tomorrow and set it up.
Easy.
Yeah.
So, you've finished your master's degree now.
Yes.
You are now Master of Science. Master of
now
Astronomy,
Master of Physics.
Master of all you see. But you're now working over at Astro Campus.
Yes.
So tell us about that. What are you doing?
Yeah, so I'm now the graduate intern for physics outreach here at the University of York. So it's lots and lots and lots of different things, working with kids from very young age all the way up to sort of 18. And a lot of the work, as Emily was saying earlier, is going over to the Astro Campus, showing people around, showing them what you can observe on a night, teaching them all about space, basically, and trying to get them interested in the night sky and observing, because it's something that's obviously, the night sky is free. You can look up at it any time. You can look and you can find lots of different constellations and lots of interesting things within the constellations as well. And I definitely think that more kids should use it as a resource. Yeah.
Do you enjoy that? Do you enjoy talking to the public and to kids about exciting space stuff?
Yeah, absolutely. I think it's really important to sort of engage with the general public as well, and just show them all about the night skies, because a lot of people don't know a lot about it, but I don't think that it's necessarily something that you can't really understand from a non-science background. It's something that everyone should learn about and enjoy. And yeah.
I think some of the ideas that Bethany has brought to us here at York have been just amazing. I remember actually it was during your interview. You showed us one of your really nice creative projects, which was pieces of paper that were then just paint splattered onto them. So you just had all these random dots everywhere. And it was like, well, just make a constellation.
Oh, nice.
It was really, really cool. And you were telling us about how tonight for the birthday we're going to be playing around with fruit to look at the scale model of the solar system.
Well, I think that things are a lot more easy to visualize when they're edible. If I'm honest, I think that it's a lot easier and a lot more interesting as well if you imagine Jupiter as a gala melon rather than what it is. And then I think the moon's something like a peppercorn, something like that. So
that's not so tempting to eat, though.
No, perhaps not. But I mean, the rest of it is.
Depends on your tastes, surely.
Yeah, true.
So if the moon's a peppercorn, what's the Earth?
The Earth is a grape.
That's great. Okay, I can see that.
That's going to go pretty quickly.
Yeah. Venus, I'm imagining, a kumquat or something? Or?
Venus is, slightly smaller grape. I haven't actually arranged something that...
Come on.
I was trying to do something different for everyone. I mean, Mars is a blueberry.
Wrong colour, surely. You can't. Well, paint a blueberry.
Well, I feel like trying to get them the same colour and the same fruit.
Are you saying I'm taking this too literally?
I think just a little bit, just a smidgen, yeah.
There's only so many parameters that you can optimise for.
Yeah.
Fair enough.
Calm down,
Fair
and we won't even start on Saturn's rings.
All right, well, that's all the time we've got for this particular episode of the Syzygy podcast. The first one where we've had a guest in the studio. Thanks really very much for joining us. It's been great fun having you in.
Such a special guest.
Yeah, thank you very much for having me. It's been great.
And when you guys have got your PhD project worked out, you've got your big grants, we can have you back to talk about that one. So
Absolutely.
The next 15 papers worth.
That's right. That's right. So, yeah, we're going to have to wind this one up. Now, Emily, if people want to get in touch with us here on the show, how can they do that?
The Tweetyverse is a thing.
Hurrah.
It's a real life thing.
Yep.
I just found out.
Yeah.
It's
we both have access to the Twitter account actually for this podcast, and I keep logging onto it and finding that you've been there first. So
but you
you're
never
taking my
know.
thunder.
You never know who you're going to get on the Twitter.
If you can guess which one of us, actually, that'd be interesting. I wonder if you can you split our tweets into two separate piles, one of which has been done by you and one of which is done by me, and see if people can tell.
Yeah, mine are the ones where you can't spell.
And mine are the ones that aren't funny. That no one get. What is he talking about?
On Twitter, we are SyzygyPod, SYZYGYPOD.
Well done. In fact, we're pretty much at SyzygyPod everywhere.
Everywhere in the universe.
You can do that on Facebook, you can do it on Instagram, all over the shop. And you can also go to our website, which is syzygy.fm, and you can get all of the past episodes and all the episode notes and all of that on there.
And so long as you are less than a light year away, you can get all of that information.
That's true. I hadn't thought about that, actually. Nice. Yeah, that's good. So where would that put you? Where's a light year away from us?
About a third the way to the nearest star.
Okay, so in another 2 years, what's the nearest star to us? Other than...
Proxima Centauri.
So anyone who's out there would be able to listen to the very first episode of Syzygy in 2 years' time.
Yes.
We're going to have to do something for that.
It's very exciting.
Although we sort of should have sent them a shout out a year ago. Oh, damn it. We didn't plan ahead. I don't know where this is all going. Look, we really should wrap this one up. Look, we will be back again in about a week or so's time for more space-flavoured goodness. But until then, goodbye from the Syzygy studios. Goodbye from Emily.
Goodbye.
Goodbye from our wonderful guest, Bethany.
Bye.
Catch you next time. Bye. Right, so this is episode 33.
33.
Keep your ears open for a good title by
And
the
a
end.
third.
33 and a third. A joke that only 6 people will get, and all the hipsters. Could do a Star Wars pun.
Oh, so her Star Wars puns are fine. But
Well, I haven't heard
my
it
fruit
yet.
puns are not.
No, fruit puns are perfectly fine in principle, as are Star Wars puns. It depends on the pun.
That was a safe for work pun, too.
It was, yeah, but you've used it once, and that's enough.
Come on, it's like my pun of the year.
Back in your corner, thanks.